we've talked a lot about your plasma membrane. We started calling it the sarcolemma for your myocytes, or your muscle cells specifically. Now we're going to go into a little bit more detail. You have within the cytosol and the extracellular fluid, you've got ions. These ions are both positively and negatively charged. Okay? And at the membrane, okay, the distribution of these ions is not equal. Okay, it's unequal. You'll see in our picture that we have quite a few positively charged ions right outside the membrane, and we have quite a few negatively charged ions right inside the membrane. Okay. This creates what we call a polarized resting state. Okay. So positive and negative poles, kind of like a battery, positive, negative ends. Okay. The fact that we keep these separated by the plasma membrane creates an electrical gradient. Okay, now we've talked about concentration gradients before, okay, where we just physically had more things in one area compared to another. Now we're going to have an electrical gradient, so we're just having a difference in charge. Okay. This electrical gradient is a type of potential energy. Eventually, we are going to use that potential energy. How do we do that? We're going to remove the barrier. Okay, now remember the barrier was the plasma membrane. We're not exactly going to get rid of the sarcolemma, but we are going to have channels and protein carriers in here. They're going to help us move these ions. Okay, when we move those ions, we're going to turn the potential energy into kinetic energy. Now, all of this is really just at the sarcolemma itself. Okay, so the membrane is charged. Everywhere else, the farther away you get from the membrane, okay, the cytosol and the rest of the extracellular fluid are basically neutral. Okay, the positive and negative ions have basically equaled themselves out. So everything else is neutral. So this energy, this potential energy, this polarization is really just at the plasma membrane itself. Okay? Now we're speaking specifically about muscles, okay, for this set of recordings, but this occurs in all your cells. We can measure how much electrical potential we have at the plasma membrane, so we can get our little gadget out, our potentiometer, and we can measure that for skeletal muscles specifically, at rest, okay, so just sitting there hanging out, the resting membrane potential is about negative 85 millivolts. Okay. Now you are probably familiar with regular volts, like a 9-volt battery, so these are just much smaller. And the negative implies that we have many more negative charges compared to positive charges. Now the negative 85 is for skeletal muscles specifically. You are going to want to remember that number. You're going to want to remember the term resting membrane potential as well. That's going to come up a lot. Okay? But you will notice that not everything is negative 85. So different types of cells have resting membrane potentials that vary. Okay? Now, how are we going to use our potential energy? How are we going to turn it into kinetic energy? We said it was going to be with the movement of the ions. Well, those ions, those charged particles, cannot just move through the plasma membrane by simple diffusion. We're going to need protein channels and protein carriers. We're going to have to do facilitated diffusion. Okay? Our first carrier, okay, is going to be the sodium-potassium pump. The name implies that we are going to pump sodium and potassium. That is correct. We're going to pump 3 sodiums out of the cell, and every time we do that, we're going to pump 2 potassium ions back into the cell. When we do this, we are actually moving against concentration gradients for both of these ions, which means we're going to need to use good old-fashioned ATP because this is active transport. Okay, so in our picture, you can see all these little purple dots. Okay, these are your sodiums. All these little blue dots are your potassiums. You can see that most of our sodium ions are already in the extracellular fluid, and yet we're taking the last few potassiums inside the cell, we're pumping them out. And vice versa for the potassiums. You can see most of the potassiums have already been brought back into the cell, but we are gathering up the last few and pumping them inside the cell. Now, why are we doing this? This sounds hard. This sounds like it uses a lot of energy. Why would we bother? This helps us restore resting membrane potential. Okay, we've got to get back to that -85 right on the dot. Our pump helps us do that.